Imagine yourself walking downtown. It's loud and it's bustling. You cross the street at the intersection and then you hear a car's horn further down the street. By instinct, you turn your head towards the sound. Do you ever wonder how we are able to hear sounds? How did you know that it was a car horn? How were you able to tell where it came from? Our ears are part of a complex auditory system, and I will go through it with you step by step. The sound is first received by the outer ear, which consists of the pinna and the ear canal. The part of the ear that we see every day is called the pinna. Its shape helps us find out whether the sound is coming from above, below, in front of us, or from behind us. Think of it like a bowl collecting rainwater. It does not matter which direction the rain is pouring, it's going to still collect water. But how can we tell if the sound is coming from the left or right? Our head plays a role by being an obstruction. Wherever the sound comes from, the ear pointing in that direction will receive the sound louder than the ear receiving it on the other side of the head. The difference in volume, combined with sound having to travel further to the other side of the head, helps the brain figure out whether the sound is coming from the left or right. Due to the tunnel nature of the ear canal, certain pitches or frequencies will get a boost in volume. The ear canal also produces wax to keep intruders away. This can be a good thing, but too much of it can affect our ability to hear. The pinna and the ear canal work together to collect sound energy and pass it on to the middle ear by the eardrum. The eardrum is like a thin piece of paper that vibrates from sound. Behind it are three of the smallest bones found in our body, called ossicles, that work together with the eardrum to convert that sound energy into mechanical energy. The malleus is the biggest bone of the three, followed by incus, and then the smallest, stapes. Now these bones are suspended in air, which is called the middle ear space. This air is continuously refreshed by this narrow tube right here called the eustachian tube that opens and closes whenever we chew, swallow, or yawn. This tube is connected to our throat at the nasopharynx, and any fluid or secretions are evacuated down this tube to keep the space clean. Any issues with the eardrum, ossicles, fluid buildup, or irregular pressure changes in the middle ear space will cause problems in our hearing. So, the sound of the car horn vibrates our eardrum. The ossicles move as the sound energy is converted to mechanical energy, and then this energy is transferred efficiently to move fluids of the inner ear. The inner ear is divided by the auditory system for hearing and the vestibular system for balance. They're both located inside the membranous labyrinth found within the bony labyrinth. We will not be discussing the vestibular today and only putting our focus on the cochlea and the auditory system. So recall that the bones are moving back and forth because of the sound energy. This causes movement in the fluids of the cochlea. There are multiple layers of membranes that exist here, but let's just put our focus on the basilar membrane. This membrane is shaped like a trapezoid and behaves like a xylophone. It moves up and down in response to the information carried by the sound energy. Basilar membrane responds to higher pitched sounds closer to the base, and it responds to lower pitched sounds further away where it is wider. The basilar membrane moves up and down with more force depending on the loudness of the sound. So, the movement of this membrane causes hair cells to move. When hair cells move, they send signals out towards the brain, turning vibrations into electrical signals, traveling up the auditory nerve. We have two types of hair cells. We have the inner hair cell and the outer hair cell. Stimulating inner hair cells do the majority of processing the sound. However, quiet sounds do not stimulate these hair cells, and that's where the outer hair cells come in. They change their shape to stimulate inner hair cells when the sound is too quiet. So hair cells send electrical signals to the brain through the auditory nerve. Electrical signals in the auditory nerve are organized by pitch. The center part of the nerve carries signals that represent low pitch, while the outer circumference carries high-pitched signals. The auditory nerve is made up of several neurons or cells that carry signals, like a bus that carries people. The pitch and loudness of the sound determine whether there is need to trigger more neurons or send signals more frequently. It's the same concept as sending more buses and trying to fit more people in each bus. The auditory nerve climbs up the brain, starting at the brainstem. The brainstem is where information about the sound begins to get processed and sorted out. We receive features of the sound, such as: is the sound source moving? When did the sound start? Where did the sound come from? Information of the sound picked up separately from each ear are also combined here. The higher we go up the brainstem towards the auditory cortex, there is more complexity to the processing of the sound and may involve other motor and sensory organs. For example, do we need to move out of the way? The auditory cortex is the endpoint of the signal, and that is where the understanding of speech and sounds take place. So, I hope you've now gained a little bit of understanding on how we hear sound. As humans, being able to hear is not only important for our communication, but it can also keep us safe from harm. Thanks for listening.